This is a quick video, or maybe not a quick video, but a video on how to find delta G for reactions, wherein we're given delta H values, enthalpy of formation, and we're given entropy values for the reagents and the products. So when we're tackling a problem like this, first of all, you must have a balanced equation. So I'm going to do that quickly using a red marker. So we can start with, for just kind of review, we see one carbon, but the H's, it's 3 plus 1 is 4, and we see only 2 here. So I'm going to put a 2 out in front to get the H's right, and then worry about the oxygens last. And we can use fractions if we need to, just for a little while. So if we count the number of oxygens on the right side, we notice it's 2 times the 1 implied is 2, plus the 2 here, that's a total of 4. But over here, we notice we have 1 and 2 is 3. So what we can do is just say, let's put a 1.5 for right now, because 1.5 times 2 would be 3, plus the 1 would be the total of 4. But to get rid of the fraction, you might know this already, you can take and replace that with 2 times that would be 3, 2 times the 1 would be 2, 2 times the 2 would be 4, and 2 times the 1 would be 2. So now we have our coefficients, and these in red are going to be really important when it comes to determining the entropy change of this reaction, delta S, and the enthalpy change, delta H, for this reaction. So let's do the first, the enthalpy, and I'm going to do that in black, using the coefficients when I need them. I know that for the calculation of enthalpy, delta H, it's really just the products minus the reagents. So we're going to say products minus enthalpy of the reagents, but we need to remember these coefficients come into play when we're talking about, that's supposed to be ENTH, enthalpy. So let's take and plug them in. Now, I've written them in that order, products first, and there's a reason why I haven't put O2 up here. O2 in its elemental form would just be 0. So we're assuming it's in gas form here, standard temperature and pressures. So we have an enthalpy of formation of oxygen gas of just 0 kilojoules per mole. But we do have our water, so we're going to say 2 times, because we have the 4 times for water. 4 times minus 241.8 plus, we're going to add to that, and that's our water. We're going to add to that the CO2, and we have 2 of those. Because heat of formation is always for 1 mole of these. Standard enthalpy of formation is for always 1 mole. So of course we're making 4 moles of water. And we're making 2 moles of CO2. And of course, I'm going to go ahead and just do it this way. We're going to do that for products. And then we're going to do the same thing for reagents down here. So this is for our products. And we'll say the reagents will be right below it. So let's do this one first. Just what would we get if we consider all the products? So this will be a little bit longer video just because it takes time. And I would highly, highly recommend, if you really want to get good at these types of problems, just practice them by doing the work. So this gives us, and I'll change it to a negative sign, 967.2, and I'm going to add to that. So I get an overall of negative minus 1754.2. Okay, but now we're on to reagents. We're going to have that we have to also consider, and it's really just the methanol, because we said oxygen doesn't have standard heat of formation of anything other than 0. So we're just going to say for our methanol minus 2 times the minus 201.2. Now we notice then this negative came from the equation, but we also have a negative value for the enthalpy change, enthalpy of formation of methanol. So we're actually going to end up with a positive. So 2 times the 201.2 equals plus 402.5. 4. So we're going to be able to add that up, and that'll give us our enthalpy for this reaction. I'll just put R for this reaction. So we get minus 1,351.8. That's kilojoules per mole. Now we're doing the same thing for our entropy. It's just going to be S of the products, no, delta S, we just say S, minus S of the reagents, but we need to remember to use those coefficients. So I'm going to set it up the same way, products first and then reagents. Hope you're getting out ahead of me. You're seeing these. I'm going to switch over to blue for the numbers. So we have CO2, I'll use water first, 4 times the amount of our entropy for water is 188.8, and I need to times that by 4. We have plus. Now these are always going to be positive. Entropy values for compounds, elements are always positive. So that makes the calculations a little bit easier maybe. Plus the 2. Entropy for CO2 is 213.8. So we're going to add all that up. 4 times 188.8 equals plus this 2 times 213.8 equals, and this sounds about right, we get 1,182.8. Now, this is in joules per mole per Kelvin, so just going to maybe just make sure you remember that this is not in the same units, it's joules, so we'll have to move the decimal place over 3 places if we're going to use these together. So our reagents, it's going to be 2 times the entropy for methanol, which is 240, plus the 3. Now oxygen does have an entropy value, 205.2. And we're going to add all that together and subtract that from this. So we're going to have a negative because this all has to be subtracted from the product. So we're getting, I'll leave it in the I'll leave it in red here, minus 1,095.6. So I'm going to write that over here so it leaves me this space here to do the final calculation for delta G. So if we take the equation there, this product's S value minus the S for reagents, we should get our S for the reaction, entropy change for the reaction. So we get an entropy increase of 82.7, and I'm just going to go ahead and write it in joules per mole per Kelvin. All right, now we have these two values we can use in that equation we need. If we're going to find the delta G for this, it's going to be delta G is equal to delta H minus T delta S. You say, well, how did you know to use this equation? Well, it's kind of implied because they're giving us S values, they're giving us enthalpy values that we're going to use this equation. So let's plug and chug, making sure to change this to kilojoules. I'll stay with it, stay in black here. So delta G is equal to delta H, so I'm just going to write that in, which is minus 1351.8. And I'm just going to say kilojoules because these terms would have actually been in moles. So those mole terms have canceled out. So it's this value in kilojoules minus at standard temperature and pressure. We say it's 25 degrees or 298 Kelvin. times, and I guess the mole term would have been canceled out here also because of those, so it's just joules per Kelvin. I'm going to change this into kilojoules. So we move the decimal place 3 places, 1, 2, and then one more place beyond the 8. So it's 0.0872 kilojoules. This is a lot of work. Sometimes your question may have just calculation of the enthalpy change for this reaction or just the calculation of the entropy change for the reaction, but you can put them together to find the delta G, and I'm just about there. Let's go ahead and do all this math we have at the bottom. So minus, I'm going to just go ahead and I'll just have, yes, we'll go ahead and use the negative, so I'll change that. 1351.8 and the negative. We're going to subtract from that, so this is going to be a negative value. Minus 298 times 0.0872 is equal to, didn't change it much, but it changed it a little bit, minus 1,000. I get that onto the page. I'll review this. 1,377.8 kilojoules of heat, or energy, is given off. This is a negative. It's favorable. Of course, burning of methanol would be favorable in oxygen. So we see that that's our final answer. And we took, again, the enthalpy value in negative, and we took the entropy value, changing it to kilojoules, times by T, but a negative out front, because it's minus T delta S. And that gave us our final delta G value for this reaction. It's not per mole, it's just for this whole reaction. 2 plus 3 to 4 plus 2 is going to give us that much energy off. Bye-bye.